We are very happy to have Sudan Xing from the University of Alberta, who's going to tell us today about Brunn-Minkowski and isoperimetric inequalities. Sudan, please.
Okay, thank you, Thomas. Thank you very much for your invitation. It's a very pleasure for me to give a talk here today. My topic is about the Lp-Brunn-Minkowski type and Lp-isoperimetric inequalities for general measures. So it belongs to the theory of Lp-Brunn-Minkowski theory. So I first give some introduce some background for this Lp-Brunn-Minkowski classical Brunn-Minkowski theory. Okay, so this work this joint work with Michael Rootson. Okay, first this is space. This space is the convex body space. So this is the background. So for this is the K0n denotes all convex bodies. That is the compact sets with non-empty interiors. So in the n-dimensional Euclidean space. Okay. So very basic, like the uniball, like ellipsoid, or the square with origin in the interior are all convex bodies. So this is the space of the this theory. So if we give this the set K0n, so naturally we hope there are some operations on this space. So because in Rn it's all vectors. So the basic basic sum is a vector sum, which is also called the Minkowski sum. So this is also the vector sum. So it means if we have two convex bodies, K and L, if we have two convex bodies, so the Minkowski sum is just all vector sums of x plus y, where x belongs to the K, y belongs to L. So this is the operation defined on this set, convex body set or convex body space. So for example, if we have this K, which is a square, and the L is uniball, you can see that obviously that the K plus L just looks like the right-hand side. So where the K is a square inside this L, so this part, and this part is just when we do the vector sum, we can obtain this larger set. This is the Minkowski sum. So we have the space, we have the operation, and we have naturally on the Euclidean in the Euclidean space, the very basic measure is called the Lebesgue measure, which also the volume. So you see the measure defined on this space, or the Lebesgue measure. So we have this space, and we have this sum, and we have this measure. So one very important inequality in this classical BME theory, which is also the core theory of this occurring inequality in this theory, which is called the Brunn-Minkowski inequality. So that is we have the sum. If we have the sum K plus L for any two convex bodies, So the volume of these convex bodies, 1 to the power 1 over n, is more than, that is, they have the lower bound of the sum of the volume to the power 1 over n respectively. So this is a very important inequality. As the big measure is also homogeneous, so we can see that this volume, that is this measure, is 1 over n conjugate respect to this Minkowski sum, respect to this operation. So therefore we have the equivalent forms, that is for any t belongs to 0, 1, we have the first equivalent forms, that is v over 1 minus t k plus t l to the power 1 over n more than or minus t v k to the power 1 over n plus t v l to the power 1 over n. So this is the first one. But we can see that these two inequality always the dimension n. We have, in fact, we have the equivalent forms, which is also called dimension-free form. It is v of 1 minus t of k plus tl, which is more than v of k to the power 1 minus t times vl to the power of t. For any t from 0, 1, this is the dimension-free forms of the VM inequality. Okay. So naturally we have the mirror, we have the sum. So of course we have the perturbations of with some IPSA, like little perturbations. So naturally, like taking derivative for this mirror, what it will become, we see derives mixed volume definition, which is like V1 of KL. So these KL are all convex bodies, so I will not read in the detail. Okay. So this when t goes to 0, that is we take the derivative for this mirror with the perturbation. You see the dimension t. So this is called the mixed volume. So we have the very important inequality, which is called the Minkowski first inequality. Let's to compare the mixed volume and the volume itself. That is, the relation is just the mixed volume of KL to the power n is more than Vk to the power n minus 1 times Vl. So the power is 1. You can see that this power on the left is n, on the right hand side is minus 1 and 1. So in fact, this is a very beautiful inequality. So if we can see for the variational formula, if we replace this L to be the unit ball, of course it becomes the surface area of the convex body. That is when the convex body itself, when the perturbation at the unit ball, we take the derivative, of course it's just a surface area. From the geometry setting, it's very obvious. So if we replace this L be the unit ball, we obtain the isoperimetric inequality. It is just the S of K over S of the unit ball to the power 1 over minus 1 over minus 1 more than of Vk over unit ball b to n to the power 1 over n. So this is just isoperimetric inequality. So this S of K is just a surface area measure for any convex bodies. So we see that for the geometry setting for Minkowski sum, just a vector sum. In fact, for any convex bodies, we have another function to describe this convex body uniquely, which is called the support function. This support function is also sublinear function. This support function is defined on the unit sphere. So that is for a given convex body K, HK for any U, if U is on this unit sphere. So HK of U is just support the supreme of X belongs to K. Oh, here is X dot product. So here XU, here is a dot product is a projection. Projection of every x on the direction u. So the support function on the direction u means the largest distance. So for example, this is the direction u, and this so here this distance is the largest distance, the projection distance for all x belongs to k. So this support function. So very importantly that the vector sum, which is the Minkowski sum, which is also can be described by the support function. That is that for this convex body K plus L, the support function on the direction of U, which is equal to the linear sum of the support function of K under U respectively for every direction U on the unit sphere. Okay. So this using the support function to describe the Minkowski sum. So of course for the function sum, naturally we have the from the L1 space to generalize to the LP space. So this generalization is very natural from the L1 space to the LP space, and which proposed by Fari and Luttwak in 1960s. Okay, so and they provided the case for p more than 1. That is using the generalization for this support function. That is so therefore the change is that changes the summation for the space is still the convex body space, and the sum becomes that the LP mean of the support function. So here is that UP is more than 1 for any two convex bodies K and L, and we have two positive parameters alpha beta. So alpha dot p plus beta dot pl. This is defined to be that that is the support. So for this convex body, this p beta dot pl. This for this convex body, its direction is just the alpha hku to the power p plus beta hlu to the power p. Then this is the p mean for every direction u on the unit sphere. This is very good definition is that this summation is closed. So this LP sum is still all convex body. Still convex body is closed space. And they also for the classical BME equality, we know that we show the volume is 1 over n conjugate related to the Minkowski sum. So for this LP case, very very interesting that also works for p more than 1 related to this LP sum. So this is called the Lp-Brunn-Minkowski inequality. That is when we have two convex bodies and alpha beta are straight positive. So for this volume of this alpha dot p k plus p beta dot pl. So here is, however, it's not 1 over n concave, it's related to the space. So this p over n concave. So this is alpha v of k to the p over n plus beta v of l to the power p over n. So this p over n concave related to this Lp-Minkowski sum related to this new operation. Okay, so this is for the Brunn-Minkowski theory. So another topic I want to mention importantly, which is called so above I talked most about our geometry about convex bodies. So next I'll talk about this about function inequality. This is called Brunn-Minkowski inequality. So which is proposed by Brown in 1975 and Bronson and Lieb in 1916, respectively. So then if we have this parameter alpha more than -1/n and t belongs to 0 to 1, if we have three functions, and if we have that this h of 1 minus tx plus ty, which is more than, here the right hand side is 1 minus t of fx to the power alpha plus t. This is gy to the power alpha 1 over alpha. Restriction we can see for h, this inside is just the Minkowski sum for vectors. Right? So this is the connection of the geometry setting. And if these three functions satisfy this restriction of this inequality, then we have the integral for this hx dx. This is also called the total mass of h smaller than, here is 1 minus t of this integral for fx dx to the power, here is alpha 1 plus n alpha smaller than t of rn of gx dx to the power alpha 1 plus n alpha is 1 plus n alpha over alpha. We can see that you can see that if h f f g satisfy the h of the Minkowski sum of the x and y with a parameter coefficient 1 minus t and t, the right hand side is alpha mean of x and gy, and then the integral or the total mass satisfy the inequality with another with the power of alpha over 1 plus n alpha. So if this alpha replaced by 0, so we can see that it becomes a classical Precomponental Inequality. So that is we raise the power 1 minus t and t for the condition and the conclusion. So for here, for the condition and for the restriction. So this power becomes 1 minus t and t. So this is a Precomponental Inequality. So Precomponental Inequality is also related to the dimension-free BM inequality. That is, if we replace this f and g, if we replace f equal to the characteristic function of a or set a, g or gx be the characteristic function of b, so we'll obtain the one volume a plus t of b more than va to the power 1 minus t times vb to the power of t. This is just a dimension-free BM inequality. Okay, so another thing very interesting that if I for this function for the condition of these three functions, the minimal function is that I can write this. You see the minimal function is that the supreme of z equal to 1 minus tx plus ty. So the right hand side is just the right hand side of the inequality of the condition fx alpha t of gy to the power alpha. So this is 1 over alpha. So this minimal function that is I can replace this star. Okay, I can replace this star, and I can replace this if and then conditioned by only one inequality. So this is later on mentioned. Okay. So now it means that we can give a new operation for two functions f and g. So this is proposed by Klatek, Bobkov, Kolosani, and Fagler, respectively, for the TS supreme convolution. That is for two functions, non-negative functions. This new summation is like first I replace this alpha by 1 over s. So here for the summation, this will becomes supreme of z equal to 1 minus dx. Sorry, this is not 1 minus t. So it's x plus y. So here is fx to the power 1 over s plus gy to the power 1 over s into the power of s. So this is the sum of the supreme convolution, and the cross product is just alpha to the power s, then f x. Okay. So this is the cross product and the sum. So that means we have the new operation for this parameter s. This GF is just the original total mass. Okay, total mass for the for a function. Very important is that if I replace this f and g by the characteristic functions, this TS supreme convolution is just the Minkowski sum. So this is because that this is just the characteristic function plus s of the characteristic function. Sorry, it's one minus t. So this is 1 minus t cross s is characteristic function a, then t cross s characteristic function b, just the characteristic function 1 minus ta plus tb. This is just the Minkowski sum for convex bodies. So therefore, we can see the this supreme convolution for functions and for functions in the functional setting. This is this f, this is summation of s, and this characteristic, the total mass in this space have the corresponding relation with the BM series space. So with the convex bodies, with the classical Minkowski sum, with the volume or the Lebesgue mirror. So besides, if we have this summation, we can derive the BBR inequality here that we have this condition and conclusion case by so this BBR inequality will becomes, so this will be 1 minus t cross s f. So that is we save the condition case. So the left hand side of h will replace by this operation of s f and g. Okay, so this will be x dx. So be more than 1 minus t. Here will be Rn of fx dx, the same power. So I just replace alpha by s, over alpha by s, so it becomes this inequality. Okay. So application of this BBR inequality, we can see that it looks like very similar to the BM inequality, because the left hand side is similar like Minkowski sum. The right hand side is like, or I can replace this power to the left to be 1 over n plus s concave of this total mass related to this supreme convolution. It's like 1 over s concave. So if I replace this measure, this Lebesgue measure by more general 1 over S can give a measure. So that is if this d mu is equal have a density phi x, which is 1 over S can give, and for any convex bodies, so we have this inequality, that is this measure 1 minus TA plus TB, which is 1 plus S can give. Okay. So this the idea is that for this for any set, the measure the mu of A is equal to the integral of the characteristic function times this phi x. So for this Minkowski sum of this A and B, I replaced this by a characteristic function of this times phi x. I replaced the so the condition of the characteristics of A and characteristics of B and characteristics of linear sum of the A and B. If I plug in the condition of BBR inequality, this holds true, so I can use the BBR inequality. So I can use this inequality. So I can obtain the show that this mirror mu is 1 over n plus S can give. Okay. So for the LP case, from 1960s to like 20 to before 2011, yeah, like we only have the support sum, like using the support function, but no one proposed like using how to use the geometry representation to show the LP sum for convex bodies. So in 1911, Ludwig and Zhang proposed a geometry description of this sum. This is that they not only propose for the convex bodies, but it also extends to all Fourier sets. So this is the all Fourier sets. So that for these Fourier sets, this LP summation is using a geometric representation for p more than 1. That is, if this p is more than 1, and we have this 1 over p plus 1 over q equal to 1, it's p q are conjugate to each other. And for any AB are two Fourier sets, the operation for this the geometric setting for this is just the union of lambda from 0 to 1 of here little complex coefficient for this summation. So it's 1 over p. This is 1 minus lambda over q. This is at A plus here this beta 1 over p lambda 1 over q of b. Okay, so this is just the union of all this kind of Minkowski sum together for all lambda from 0 to 1, or I can write more clearly. So this is just okay, alpha 1 over p 1 minus lambda 1 over q over x plus beta 1 over p lambda 1 over q y. This x belongs to A, y belongs to B. Okay. So this for all Fourier sets, this definition works. This is a new definition for the LP summation using a geometric setting because it's related to Minkowski sum. So when this AB are the convex bodies with origin in the interior, so it recovers definition by Fourier and Lutok using the support function of P. As we can show the support function of these two. In this case, this sum is not only a convex body, but it also have the same support function. by Alfari and Lutwak using the LP-mean. Yeah. So one important thing that the LP-BM inequality, there is a volume P over N can give related to the LP summation. Here it also works for compact sets, compact Fourier sets. So that means for like this, if this set is not convex, but it's still P over N concave, that is still this volume, still P over N concave related to this sum, this new sum using the geometry setting. So we have the question that what can we do for this new geometric sum in the LP setting? Or can it be generalized to the functional case? So our answer is yes. Yeah, our answer is yes. This work with it's our work with Michael Wilson. First, we generalize the BBR inequality in the LP case. LP case that is let P more than 1 and PQ are conjugate each other. And this S is non-negative. If FGH satisfy the restriction, the condition is not originally linear Minkowski sum, very simple coefficient, and now it is 1 over P. This is 1 minus lambda 1 over Q is X plus T1 over P lambda 1 over Q of Y. So here is more than 1 minus T 1 over P 1 minus lambda 1 over Q Fx to the power 1 over S, then T over P lambda 1 over Q G of Y over S, then to the power S. So the condition of the three functions FGH becomes like this. This holds for all lambda belongs to 0, 1. If this restriction for H holds, so total mass of H, F, G, F and G satisfy the following inequality. So this HX dx and satisfy 1 minus T of Rn. So this Fx dx, this P n plus S. So this T over N dx to the power P n plus S. Then here is N plus S over P. So we can see if F, GH satisfy the above inequality for all lambda from 0, 1. So we can show the total mass is P over N plus S concave for the integral. Okay. To give the proof, because our main point is that we show for all S is positive case. So to the main idea of this proof is that first we show that if this S is a positive integer, so if FGH satisfy the condition, we have the following inequalities. So in fact, the idea is to connect the function to the convex bodies or convex sets. So for any convex body F, we consider the n plus s dimensional body of revolution, that is AS of F, which is equal to xy. So this is ns plus n plus s dimensional convex body. X belongs to the support of F. Normal y is less than fx to the power 1 over s. Then this is the convex body of n plus s dimensional. So if F and G and H satisfy the condition of this LP-BBL inequality, we can show that this body resolution for H is contain the body the LP sum the LP sum of this LP sum of this the body revolutions of F and G respectively. Okay, so this is the most important part for the P case. This is P. So because this goes back to this all belongs to the convex body of n plus s dimensional convex body. So because for the convex bodies, we can use the LP-BM inequality. So that is, we can show the volume of this convex body, which is n plus s dimensional, P over n plus s conjugate, 1 minus T, the volume is ASF. And so this is a geometric setting for the for the body of revolution. Besides, we know that the volume of this for any convex bodies, the volume of this body of revolution is just equal to the unit ball of the s-dimensional unit ball times the total mass of this function dx. So if we replace this n plus s dimensional the big matter of this body revolution by this formula, so you can obtain the inequality related to this total mass. So obtain the inequality. So that is here. So we show that for when s is a positive integer, this inequality, this LP-BBL inequality holds true. So the next step is that if this s is a quotient number, we assume that this s equal to L over M in the lowest terms. So we construct the new a multiple function x. So this is x1 xm. This is the course multiple function. And consider the nm plus L dimensional body of revolution. So this is just for original one. This x belongs to the support of F. This is the Rn. So this is Rs. So first, okay. So here, for this x, which is belongs to the support of F to the power of this the quotient product of M is the denominator of this quotient number, and for y is still less than fx to the power of 1 over L. Okay. So this convex body n times m plus L dimensional convex body. So of course we can use basically we can go back to use this this LP-BM inequality here for this in the second step. Similar, we can show this LP-BM inequality also holds true, and then similarly goes back to the total mass of the function. So obtain that when this s is lowest terms, when this s is a quotient number, this LP-BBL inequality also holds true. So the last one, when this si, we can choose a sequence of quotient number to approximate any positive number. So we can show this LP-BBL inequality holds true. So this is the main idea of the proof. So I will not. The idea is same, but the most important difficult part is to show these two steps. It's true because in LP case, the Gaussian product is much more complicated. Okay. So similarly, for this restriction, this restriction of this condition, we have the we have the minimum function that HPZ is equal to the supreme of Z equal to 1 minus T1 over P 1 minus lambda 1 over Qx plus T1 over P lambda 1 over Qy. So here the lambda belongs to 0, 1, and the right hand side is just 1 minus T1 over P 1 minus lambda over Q Fx over S plus, yeah. So similarly, like the L1 case, so we can define this new operation that is the LP supreme convolution. That is, we introduce this operation LP supreme convolution. That for any alpha, beta, and negative of two functions, supreme convolution is just changed with much more complicated coefficient. Okay, so this is okay. I think this is okay. So this is the LP supreme convolution. We can also show that it's also closed space. Okay. Importantly, if I replace the f be the characteristic function of a set A, G be a characteristic function of B, so the 1 minus T, 1 minus T, the LP supreme convolution of f of these characteristic functions becomes a characteristic function of the Lp-Minkowski sum using the geometry definition, that using the union case of the lambda from 0 to 1, and then the Minkowski sum together. So we can show this LP supreme convolution and Lp-Minkowski sum have the corresponding this is the function space with this PS operation, and we have the total mass measure. And for the Lp-Minkowski sum, the Fourier set space with the sum and with the volume space have corresponding relation. So the LP-BBL inequality can also written as that here will be Rn. This will be 1 minus T cos PS of F. Using this LP supreme convolution to replace the three conditions H, F, and G, replace the H condition. So this will be T cos PS of G. Here this is X dx more than. So Rn fx dx is P over n plus S plus T over Rn dx dx P over n plus S, then n plus S over P. Okay, maybe I can write on the left by the same thing. So we can show that this total mass is P over n plus S can give related to this LP supreme convolution. Okay. So similarly for measures, the application of this LP-BBL inequality that when this P is more than 1, S is positive, mu is similar, over S can give. For any barrier sets, we can show this measure mu is also P over N plus S can give. So this is 1 minus T dot PA plus T dot PB. This is P over N plus S can give. Okay, so 1 minus T mu A is P over N plus S plus T mu B to be called P over N plus S. The similar idea of the proof as mu A be the mu A is just the integral of the characteristic function times the density function. And we can show the characteristic function of 1 minus T dot PA plus T dot PB x times phi x and one characteristic function of phi x and one characteristic for bx phi x. These three functions satisfy the condition of the LpBBR inequality. So yeah, so we can obtain the LpBM inequality for measures. So we know that for the variational formula case, we obtain the mixed volume and have the mixed volume inequality. Similarly, we have the LP case related to the measure. Okay, so this one IPSA goes to 0. So this is the integral for F plus PS, IPSA equals PS G. So this is not this is a more general measure instead of the big measure dx. Okay, mu for IPSA. So related to the LP supreme convolution with this new operation, and if we obtain the similar Lp-Minkowski first inequality for measures, for S is non-negative, F is a differentiable invertible function. If Ft is concave related to this LP supreme convolutions, we obtain this inequality. The isoperimetric case is that if the F and the integral for F and G are equal, so obtain the following isoperimetric inequality. So when this d mu is just a Lebesgue measure, so we can obtain the following inequality. Of course, it's similar. Similar, it's just the color is very similar. So also give the results that when this mu is a product measure, or for different case for S with one S to be negative, of course I can give a case of when one S equals to 0. We're talking about the Precomponental Inequality cases. So as time limit, I'll not show the detail. Okay, so this is all my talk today. Thank you very much for your